Swayam Prabha. Digital India. Educated India.
Hello everyone. Today we'll start our 21st lecture. And in the 21st lecture we'll try to constitute phase diagram, of course a simple one, from free energy composition diagram in case of binary system. Now, in the last two lectures we have talked about phase diagrams, and we have also seen different kinds of phase diagrams in case of solid to liquid transformation, in case of solid solid transformation. In case of solid to liquid, we have taken example of isomorphous system where both the components are completely miscible in liquid as well as in solid over the entire composition range from 0 to 100% of the 0 to 100%. And the second one we have talked about eutectic system, which one is also talking about liquid to solid transformation, and there we talked about transformation of one liquid to two different solids. And then we also talked about peritectic transformation where liquid plus another solid, they react together and forms another solid of different structures. And then finally we talked about eutectoid transformation, which talks about a solid transforming to two different solids. And these transformation points, as we have seen, that the degree of freedom is 0, which means that these points are invariant points. And then we drew a phase diagram for iron carbon system, and in that iron carbon system we saw three different reactions. One is eutectic, another one is peritectic, and there is another one which is eutectoid. And we also saw that there is a steel part when the carbon content is up to 2 weight%, then it is called a steel part of the diagram, and then from 2 to 6.67% carbon we call it a cast iron range. And in that particular phase diagram, if you notice, if you go back to lecture number 20, you will see that there are different phase zones, and out of those phase zones you will see that we will be looking at the eutectoid part, and the eutectoid part would be useful during the heat treatment of steels, and that particular different heat treatments are there. For example, annealing, normalizing, hardening, then there could be spheroidizing, there could be heat treatment like Aus-tempering, Mar-tempering. There are different types of heat treatments. Those will be only concentrating on the steel part of the phase diagram, and that too the eutectoid section, and it would also try to consider most of the cases it tries to consider these heat treatments would try to consider the eutectoid reaction. So, that means one solid converts into two new solids, and in case of steel part we have austenite going into cementite and ferrite, and these transformation would actually gives rise to a huge number of microstructural variations, and that actually affects the material's properties. And another part, it is important that we have drawn that particular diagram on the basis of Fe3C presence. Now, this Fe3C is a metastable phase, and the stable phase in case of iron carbon system is iron, and the another one is graphite. Okay. But Fe3C is forming, and Fe3C actually, if you give sufficient time and also in the temperature range required for breaking of Fe3C, then Fe3C can break into two parts, one is iron, another one is the carbon, and that carbon is nothing but the graphite. And in case of cast iron, actually we try to break this Fe3C into iron and graphite, and that is why you get different types of cast iron. For example, one is grey cast iron, then another one is spheroidal cast iron, or we call it SG iron, and there could be another variety which is called malleable cast iron. And in case of the cast iron where we have Fe3C present, that means the metastable phase which is present in cast iron and the carbon content is more than 2%, that time that particular cast iron we call it white iron. So, but we are not looking at that part, but we just would like to mention that the iron carbon phase diagram, in case if it has Fe3C presence, then it is called metastable phase diagram. So, now we have just described those things. Now, today our intention would be to find out phase diagram from free energy and composition plot. So, free energy and composition plot can be derived from the consideration of ideal solution, or you can also extend it to a real solution, but that part we are not going to discuss in greater detail. Rather, we will straightway come to see how this G versus X plot look like in case a situation where it is an ideal solution. Okay. So, in case of ideal solution, whenever we are talking about ideal solution, we mean that del H mix, that means enthalpy of mixing, is 0. So, that means whenever two elements are mixed together, when they form a solution, it can form either liquid solution or solid solution. That time this particular term would be 0. It means that the interaction between the components is 0. So, A and B. So, if A metal and B metal are joined together or mixed together, if they form solid solution, let us say they form isomorphous system. So, that means in the liquid as well as in solid, in both the cases they have complete solubility. So, that time the interaction between A atom and B atom is 0, and that particular condition we will consider, and that case the diagram for G versus X, X is basically mole fraction. Mole fraction, it has a nature like this. Okay. So, it could have a different nature, it could have this, it could have this. So, but you will see that it is bending towards, it is a curved nature. Okay. And this says that if this is 100% A and this is 100% B, and if they form solid solution or liquid solution, means we are considering isomorphous system, that time this is the percentage of Xb or the mole fraction of B is gradually increasing. So, this is Xb would be 0 here and Xb would be 1 here, because finally both the things when they are mixed, then Xa Xb equal to 1, since it is a fraction and it is a binary system, A and B. So, binary system. Now, if this is the graph, this graph tells that at any point on this graph indicates some free energy value, and that free energy value can be found out from the tangent on that particular point over this graph. Okay. So, if I try to find out free energy at this point, so this point, for example, this is 2 G2, and the free energy would be, if I draw a tangent, see if I draw a tangent, and this tangent value would intersect 100% A and 100% B at 2 points, and this particular point we call it as mu A, and this particular point we call it as mu B, and this mu is nothing but chemical potential. Chemical potential. And if this composition corresponds to X0, means the composition of Xb equal to X0, then we can take an equation for this straight line, and that equation becomes this is that equation of this particular line. This is a straight line because there is a tangent over this graph. Now, if I try to find out what is the value of G2 prime, that means the free energy at this composition, again I have to draw a common tangent, sorry, not common tangent, a tangent on this line, on this point, and it will cut here. So, this is a new mu B prime, and this is mu A prime. And whenever we have this graph, since we are considering complete solid solution, it is a graph for a particular phase, and let us say we consider that it is a graph for solid. Okay. Now, that means at any point, if we try to draw a tangent over this graph, then these intersection points will be the mu values with the chemical potential of that particular component at this composition. Okay. For example, if I try to find out what is the mu of B, that is the chemical potential of B, the chemical potential of B would be at this composition would be this one, and this chemical potential would be for that particular phase, which is S solid, and similarly this is also for S. Similarly, in this case, if I try to find out what is the chemical potential of solid, chemical potential of A in that solid, then this would be my value, and that corresponds to this composition. Now, if I try to just for and that means here also we can make a change, this would be for solid, this is for solid. Now, similarly I can have plot for liquid free energy over this entire composition ring, because we are assuming isomorphous system and where liquid solid solubility would be there from 0% B to 100% B. And here also I can have a graph like this. So, this is liquid, and similarly if I try to find what would be my chemical potential of A at this composition in liquid, so then I have to just draw a tangent again on this point over this liquid graph. This is the liquid phase, this particular red graph which is G versus X plot for liquid phase. So, this would be mu A and this is the liquid, and similarly this one would be mu B liquid. So, like that way we can find out what is my equation for the free energy at any point over this graph for a particular phase, if we know these two values, okay? Because this composition we know, these two values we know, and we just put it here and find out what is the equation for this straight line. Now, just for sake of understanding, this information would be useful later on when we try to find out the free energy difference for the transformation, when we talk about a transformation from solid to solid, okay? And every time in order to find the nucleation rate, we need to find what is the free energy, volumetric free energy change, which is actually giving the driving force. So, that will be required, and for that we need to find out if this line is given by this particular equation. I can also find out, if I try to find out what would be my G2 at composition, let us say x 0 prime. So, this composition is also lying on the same line, same tangent. So, I just would shift this equation, because these two term will not change, because it is on the same line and these two are the two fulcrums, okay? So, now if we try to plot at x b equal to x 0 prime, we have to just simply 1 minus x 0 prime mu a s plus x 0 prime mu b s. So, what I am doing? I am just shifting my point from this place to this place. Equation does not change, only thing is my composition is changing. My equation remains the straight line equation, these two variables remain same, these 2 points, only thing is I am changing the composition. If I do this, I am actually indicating the same free energy line, okay? And what does it mean? It means that on this line, I can find what would be my G2 at any compositions over this line, okay? Now, if I have this information, if I have the liquid and solid, then let us see an interesting situation. This is my liquid, let us say this is my solid, and let us say this is my liquid. Now, this is 100% A, this is 100% B. Now, if I draw a tangent at this point, so that means this is mu A S, this is mu B S at composition x 0 S, and this is percentage of B, which is in the form of xp. This is the mole fraction. Now, if I try to draw another free energy, another tangent over this point, this is x 0 liquid, let us say x 1 liquid. So, now this value would be mu B liquid, and this is mu B solid. Sorry, it is a liquid phase, because this line indicates the liquid. Now, when would you think that the alloy or the solution of this composition would you think that solution of this composition and solution of this composition would be in equilibrium? Can they be in equilibrium? They cannot be in equilibrium, because here it is G2S and here it is G2 liquid, and G2S not equal to G2 liquid. So, this is not the condition for equilibrium. And equilibrium means del G, which is G2S minus G2L, should be 0. And we know that these are all drawn at pressure constant, and let us say 1 atmosphere, and this is drawn at a particular temperature T, and we can change the T, and accordingly this graph would vary. Either it can shift downward or upward, those things can happen. So, when would you think this thing can go to 0? This is only possible if we have a common tangent. So, that means if we draw a tangent over this particular graph and that tangent cuts the other graph at some point, so then you can see, so it has cut the solid line here and the liquid line here. So, these 2 points, that means here we can find out G2S and here also we can find out G2 liquid. And interestingly, the equation for the line, so if I consider this is, so equation for this line, if it is solid, I can make this equation, which is G2 solid. Let me do it in yellow because I am giving a yellow line for the common tangent. G2 solid would be, this is the composition, let us say this is X0S and this is X1L. So, 1 minus X0S mu A solid plus X0S mu B is solid, and this is G2S, G2L equal to 1 minus X1 liquid mu A liquid plus X1 liquid mu B liquid. So, that means these 2 equations are indicating same line, and then if it is same line and you see that these 2 terms are, so I can, if I take this one, I can, as per this particular shifting of points, I can also shift there, and that time I can write G2S equal to 1 minus X1S. If I take this composition to this composition in case of solid, so I can write that as per that conversion. So, from this, now you see, if I try to see G2S minus G2L would be equal to 1 minus X1S XAS minus mu AS minus mu A liquid plus X1 this composition is liquid. So, solid, initially solid, but I can also take it as liquid because it is telling the same composition. So, I can convert to liquid. Similarly, I can convert this one to be liquid. Mu B S minus mu B liquid. So, these 2 terms are same values and these are giving the same line. So, these value becomes 0, okay? And then when can it be 0? Because these 2 terms are not changing, only thing is if separately mu A S equal to mu A liquid as well as mu B S equal to mu B liquid, That is the condition for equilibrium. So that's why people say, that's why it is said that common tangent gives the equilibrium. Now if I draw the equilibrium, if I try to draw equilibrium at different temperatures, I could get the phase diagram for isomorphous. Let me draw that. So let's draw an isomorphous phase diagram where it's a liquid solubility and solid solubility is there from 100% A to 100% B. Now if I try to draw the free energy composition diagram for liquid and solid phase at this temperature T1, since at this temperature T1 liquid is stable, so the free energy of liquid graph will be below solid free energy graph. These are all free energy composition graph. This is the composition, this is free energy. Now liquid free energy graph is below solid free energy graph at all the compositions, and it means that the liquid would have lower free energy of solid all the time from 100% A to 100% B. It also means that the liquid would be stable, as we have seen that the free energy, the lower free energy substance would be stable compared to the higher free energy thing. So now over this entire range we have liquid. So that's what we are seeing, from this composition to this composition, everywhere it's a liquid phase. Okay. Now this is at temperature T1. As we have seen that at different temperature we can draw the composition free energy graph from, if we know the mu, which is the chemical potential. Now if I try to see what happens at this temperature, which is the melting point of TMA, that means the melting point of pure A. So whenever we reach that point, it suggests that if it is 100% A, a first solid would appear in the liquid, and that would be 100% A if we take this composition. So we have to take this composition. So then the graph nature looks like this. So at this point both the phases have the same free energy, as we have seen before that if we have G for a particular single component system, this is the graph we have seen, this is G liquid, this is G solid. So this is my Tm, which is the melting point. Similar thing happens here. So that means both the phases would have same free energy at this point. That means the free energy difference is 0. So here I would get first A, okay, the A, pure A would start coming out in the form of solid. So that means here if I try to see at this point I would get the first solid, but apart from this composition, rest of the compositions liquid free energy is below solid free energy. So liquid would be stable. That is what we are saying. Apart from this, rest all compositions liquid is stable. Now come back to the composition situation where we are taking T2 for the entire composition range. And the T2 we see that once if we take any composition within this range, any compositions, if we take any composition, that composition would distribute into a liquid and solid phases, and that particular liquid, and the composition of solid would be this one and the composition of liquid would be this one, and these two phases are in equilibrium. Why? Because the common tangent if we draw this common tangent for liquid phase and the solid phase free energy, I see that these two compositions are in equilibrium because they are falling on the same line and this condition is satisfied, and then we say that these are in equilibrium. Okay, similar situation we can also see here at T2. So that means if we see this particular diagram nature, along this common tangent, this composition and this composition both are at equilibrium because they are falling on the same common tangent. And then what does it mean? That below this you see all the solid free energy graph is below liquid, below this composition if we see, and on the right side all the liquid composition, because this is liquid graph, is below free energy for liquid at different composition between this to this, liquid is below the solid. So, left to this all will be solid, right to this line would be all liquid. So, that is what we are saying, that left to this all are solid and right to this all are liquid. So, and what happens in between? In between, the liquid is distributed into solid and liquid of these composition X0S and X1L. So, this X1 is the composition for liquid and X0 is the composition of solid. So, that is what we are saying, this is X0S and this is X1L. Now, once we come to TMB, this particular temperature, we find the situation becomes like this, where everywhere I see that the solid free energy curve is below the liquid free energy curve. So, that means the solid free energy would be lower than the liquid free energy and solid would be stable over the entire composition, but at this point these two lines are cutting, which is 100% B, and 100% B case the same situation is taking place. So, here the B would appear, the B solid would appear at this composition, and that means 100% B composition, if we take, this would be my situation where at this temperature B would start coming if we take 100% B. So, here both the liquid and solid free energy lines are matching, and rest of the places everywhere solid free energy is below liquid free energy, and rest of the cases everything would be solid. So, this is my melting point of B and rest all is solid. Now, once we come to T3, you see the solid free energy at all the compositions is lower than liquid free energy, and that is what we have, all the solid, no liquid anywhere, and we see it is all solid regions. So, that way we try to draw a composition free energy diagram, and from that we can derive a phase diagram. Okay. So, now this particular thing you can also take it to draw eutectic phase diagram, you can also draw eutectoid phase diagram, you can also draw peritectic phase diagram. Okay. So, you can see that how we can draw phase diagram from G versus X plots. Thank you.